We'll now take a look at parallel programming. We've discussed before about how the complex scientific problems of the 21st century are testing the limits of the von Neumann architecture for sequential processing. So what we're saying here is, these large-scale computing problems are becoming too large for normal programming approaches to handle it. We can't use the normal approaches that we're accustomed to. So this is where parallel processing comes to play. So this is really a catch-all term for a variety of approaches to computing architectures and algorithm design. So if you remember, there were two different models. So we're just going to take a minute to review those two models of parallel architectures. So we have the SIMD model, which stands for Single Instruction Stream, Multiple Data Stream. And the idea with this is we have a single control unit that broadcasts a single program instruction to multiple ALUs, all of which would carry out that instruction in unison. And this is usually globally shared data as well as private data stored in local memory. The second model was MIMD, or Multiple Instruction Stream, Multiple Data Stream. And the idea with this is that we have these interconnected processors that independently execute their own programs on their own data, and they communicate with each other as needed with the other processors. So the MIMD model actually includes a number of different structures, such as multi-core computing, where you have two or more processors packaged together on a single integrated circuit. Most of your computers probably now either dual core or quad core. There's also cluster computing, where we have independent systems such as mainframes, desktops, or laptops that are all connected by a local area network like an Ethernet or a wide area network. Let's give a very simple example of doing something with SIMD parallel processing. Now, we talked before as an example where we can add a value to each item in a vector. So here we're going to add k to each value in a vector, which we denote as v, of size 6. So we're saying our vector has 6 items in there, 6 values, and we're going to add k to each of those. And we're going to assume that we have 6 ALUs, and we're with IDs 1 through 6. And each ALU is going to have its own local or private data that consists of one of the elements in V. So this is what our code would look like, something like this. So we would say k is public. This is a value that we're given that we're going to be adding. V is this private data that we're only going to be able to do some stuff with. But the parallel part of the code is this section right here. So the parallel 1,6 v equals v plus k. So what this is saying is that in parallel for each of the ALUs, we're going to take the value of v. So each ALU is going to have one of the elements of the vector, and that's going to be denoted as v. And we're going to add k to it, and then store that back into v. So here we're saying that each ALU would execute the same instruction in unison, but each one is done on a different element of v. For the MIMD model, let's take a look at an example. Here we're going to try to find the largest number in a list. Now the way we're going to do this is we're going to use what's called a divide and conquer approach. So instead of looking through every single item sequentially to find the largest item, we're going to split the problem into smaller pieces. And for each piece, we're going to send it to another processor. So we're going to keep splitting and sending these pieces until each processor's task is very trivial, where there's only a single item in the list. And then when it combines back together, we would actually get the result. So the idea is that each processor would complete the operation, and then it's going to return the result to the processor that sent the task. So the idea with this is we'll split up all the tasks so that each processor would have one number. Well, if it's just one item, that's going to be the largest value. So it's going to send that value back to the processor that sent that piece. And then the sending processor is going to get the largest items of the values that it sent. And then it's going to determine the largest item from that set. It's going to then send that largest value to the processor that gave it the list, and it's only going to return one item, and we're going to go back this way. So the whole point here is that these processors are going to do a little bit of work, and then it's going to send the results all the way back to the original processor. So instead of a single processor doing all the work, we're just divvying it up among all the other processors. So they each do a little bit of the work, and then they just send the results back. Now this does require a lot more communication among the processors, but it it doesn't take as much time compared to the actual processing. Let's walk through an example of this just to kind of help illustrate what's going on here. So let's say this is our original list, 5217860. Clearly, if you take a look at this, you can see that 8 is going to be the largest value. But let's look at how we get to that. So the first thing is we're going to split up the list. So we're going to just split it in equal halves. So processor 2 in this case, so processor 1 originally had the list. So processor 2 is going to have the list 5217, so it'll have the first half. And processor 3 is going to have the second half, the 8, 6, 3, and 0. We're then going to split the lists again. So we're going to send the broken up lists into other processors. So processor 4 would have 5 and 2, processor 5 would have 1 and 7, processor 6 would have 8 and 6, processor 7 would have 3 and 0. And then we'll split the lists one more time, so we would have additional processors, and each one would have one item in the list. So processor 8 would have 5, processor 9 would have 2, processor 10 would have 1, processor 11 would have 7, 12 would have 8, 13 would have 6, and so forth, 14 would have 3, 15 would have 0. So now that we've divided up the entire list, what we can see from processors 8 to 15, the task is very simple because it's just one item. So for each processor, it's going to conclude that, well, since there's one item in the list, that must be the largest item in that list. So what it's going to do now is it's going to send that value back to the processor that gave it the information in the first place. So we'll have processors 8 and 9 send their largest values back to processor 4. But in this case, 5 is the larger of the two values, so processor 4 is going to store 5. We'll then have processors 10 and 11 send their results back to processor 5. Well, since 7 is larger than 1, processor 5 is going to store 7. Processors 12 and 13 will send their values back to processor 6, and in this case, 8 is larger than 6, so processor 6 is going to store 8. Processors 14 and 15 are going to send their values back. 3 is larger than 0, so processor 7 is going to store 3. We'll now have processors 4 and 5 send their results back to processor 2. So since 7 is greater than 5, processor 2 is going to store 7. We'll then have processors 6 and 7 send their data back to processor 3, and since 8 is greater than 3, processor 3 will store 8. And then finally, processor 2 and processor 3 are going to send their results back. So here, 8 is greater than 7, so processor 1 is going to store 8, which is in fact the largest value in the list. So notice that what happened here is we broke up our list into smaller lists, we determined the largest values, sent those back to the previous processors, and when we finally got all the way back to processor 1, it has the final result. Now let's talk about how much of an improvement this is compared to the sequential approach of just checking every single item in the list. Now, let's say we have n items in the list. So that means the n numbers are divided into two halves at each step. This means we have log base 2n sets of splits. This means that to divide the data, it's going to take theta of log n time. Now remember, I think we said before that if we say log n, we basically mean log base 2 of n. But so this takes theta of log n time to divide the data. That also means that sending the results back in parallel also takes theta of log n time. Therefore, the total running time is theta log n. And the reason why this is important is because, if you remember, the sequential approach is theta of n. So this is significantly faster than the theta of n time approach of checking each item in the list. I mean, if you just do the comparison, I think we did a comparison not too long ago, just comparing like log n, n squared, and 2 power n. And you might want to go back and check that again, but you'll see that log n is much faster than n, especially for large values of n. We'll conclude the lecture by introducing some new languages. You might think that we've discussed all the programming needs out there, and the fact that they've been met with the existing languages. But this isn't true. There are new languages and new paradigms continue to be developed even to this day, even with the hope of maybe finding that silver bullet of an easy-to-use, efficient, general-purpose computing language that will enforce the good programming practices to allow a quick production of error-free code on all the platforms. It's wishful thinking, you never know. So what we're going to do here is we're just going to briefly look at two relatively new programming languages. One of them is called Go, and the other one is called F Sharp. Go is a programming language that was developed at Google in 2009. The original idea behind it was there was this frustration with existing languages and environments for systems programming. You basically had to choose between efficient compilation, efficient execution, or ease of programming. There wasn't really a language that had all three. So with Go, there was an attempt to combine several of these ideas. There was an attempt to combine the ease of programming of an interpreted dynamically typed language with the efficiency and safety of a statically typed compiled language. The way that I would go about describing it is just think of it as trying to combine the best aspects of C++ and Python. Now, Go is an open source language, so the source code is available for anyone to examine and use. And then the changes or additions can also be proposed. It's also noted that the target areas for this language are for systems programming and programming for multi-core machines. So Go is actually in use to support several Google internal projects. F Sharp is a new language developed by Microsoft, and this was developed in 2005 and is now included as a language in the Microsoft Development Environment Visual Studio. In contrast to the open source Go language, F Sharp is a proprietary language, meaning its intellectual property belongs to Microsoft. Now, it is primarily a functional language, although it does have some object-oriented characteristics and some parallel programming characteristics. And because it is supported by the Microsoft .NET framework, it does have access to all of the common libraries of .NET. Let's take a look at an example of a program in F Sharp where we're going to compute the sum of a list of numbers. In fact, this is the same approach that we did with our scheme example, where we have a list of numbers and we want to get the sum of it. So here's the code in F Sharp. The let here is similar to our define statement that we had in scheme before. And rec means that this is going to be a recursive function, and sumList is the name of the function, and then x is the argument of the function. So the whole point here is that we're going to check the input x with two possible choices. That's what the match x with part is. We're comparing x with two possible choices. One choice is if x is the empty list, which is the empty square braces that we have in our code. And the arrow to 0 means that we would return 0. Now, if it's the other one, so if x has the form y : z, which is the notation that we use for lists in F Sharp, then here we're saying that y is in the front of the list and z is the list itself. We would return y plus sumList, and then z would be the argument of this function call. So let's actually do an example of calling this function and see what would happen. So let's say we would enter sumList 3, 4, 5. So this is the notation that we would use in F Sharp to denote a non-empty list. So following the logic we've done from before, we would see that the list is not empty. So we would get 3 plus sumList 4, 5. And then so when we call this, the list is not empty again. So this would end up being 3 plus 4 plus sumList of 5. We'll call this again 3 plus 4 plus 5 plus sumList of an empty list. And since the list is going to be empty, when we call sumList here, we're going to return 0. So we would get 3 plus 4 plus 5 plus 0. And this gives us the final result of 12.